Okay, so previously we looked at the linear regression model, and it's a convex. We had a convex loss function to minimize. It was so nice, so we were able to derive the closed form for our parameter W. Okay, and here, as you can see, we had two different equations. So the first one, we defined our loss in function of W and B, but then we proposed a closed form. Sorry, we proposed a compact form where the W tilde is defined using B scalar value, or the bias, and the W vector, the weight vector. Okay, so now what we'll look at is minimizing a non-convex regression problem, or a nonlinear regression problem. So to do that, we specifically will look at the case of the what we call logistic regression, which is a classic nonlinear and non-convex problem in machine learning. And the logistic regression, basically, it is defined using the logistic sigmoid function, as you guys can see here. So this is our sigmoid function. And what is the hypothesis that we are making about our input data X and our target output Y? So we hypothesize that if we want to use basically the logistic regression, the relationship between the output and the input, it should fit what we call a logistic curve. Okay, so their relationship, as you can see, is nonlinear. Okay, and they can easily be written in the function of this, what we call a generating function right here. So our generating function is the sigmoid logistic function, and in such way we can define our logistic regression problem. So, but imagine if we have a linear relationship between the y and the x, we don't need to use this. So basically we use the logistic regression model when the y depends on the x by fitting this logistic curve. Okay, so here let's look more closely at this logistic function. So what does it do? So the basic idea is this model was designed to model the population growth over time. So the population growth is like what we call the sigma t of t, and t is the time. So depending on the time, we will see that a specific population will have a small number in the beginning, and then a big increase, and then it kind of levels off, or the system gets saturated when it reaches a value, a specific time point, t cross. So this models the growth of biological systems, where generally we hypothesize, or we say that the growth will stabilize and level off due to a lack of limited resources. So maybe lack of food, lack of space. So it's not possible for these, for the population to keep infinitely growing. That's not possible because we have limited resources. So at some time point, the system will basically stop growing, and this is the maximum concentration or growth for our population that we will get. Okay, so here we can also look at the sigmoid function, and we can add what we call a scaling, like a weight parameter, a scaling parameter, and this parameter W, it will tell us about the transition that the x variable is doing in function of our target y output, or in this case we have the time in function of the population growth. Okay, so if we have the W is equal to 1, then we have the red curve, and that's the typical sigmoid curve, okay, the conventional one. So at 0 we have 0, at 1 we have the value 1, and in the middle here it's usually 0.5. Okay, and then if we have a larger weight, so we can see that the transition becomes sharper. So the system quickly saturates. Okay, so it saturates faster. So the T here, the saturation T is like it comes earlier than it's smaller than the saturation of the red curve right there. Okay, so which means that we say that the system saturates faster, and the transition here is very becomes more like sharper. You can see when we go from the red curve to the blue one, as we increase the W, okay, we can see that we're moving from a soft transition, very smooth and soft, to a very sharp one right there. So this sharp transition, it kind of looks like a step function. So if you guys remember, this is how a step function looks. And so basically you can see that why this is important, because the W here can capture different data distributions. Because imagine in this case, for example, we have the W is equal to 1. But if we have this distribution of our data, so we plot our data, let me select another color, maybe this one, okay, purple. So this is our data, but right here we can see that like somehow the decrease is like much sharper. Okay, so the curve that fits this data is more, it will look something like that. Okay, so the W here needs to be larger, so larger than 1, so W maybe equals to 2. So we need to adapt the sigmoid function to our data, right? So imagine also if our data is a bit shifted, so which means like if we shift these curves slightly to the right, oh, I cannot move this, no, it's fine. Okay, so it's moving a few things around, but imagine if the data is shifted. So if we shift it by a plus b, so we have WT plus b, okay, so this means that we're translating the data by a b factor, okay, then we need to take this into account. So our sigmoid function will look something like this. So we have our sigmoid WT plus a translation or a shifting factor B. And why we're finding by finding the W and the B, we can perfectly fit the distribution of the data that we hypothesized that it was generated or spanned by a sigmoid function. Okay. So here, let's look at this case. So given a data set, so we have our training data set xi, yi, that is distributed like a sigmoid function. So these are all of our points. For example, here we have xi and ground truth yi. And we can see by just plotting the data, we can see that it fits a sigmoid function with a scaling factor W, some scaling factor W, and maybe some shifting B, okay? So our sigmoid function might look like something like this. So it's like smooth to smooth. Right, so this is our fit to the data. So the sigmoid function in this case will depend on two variables, W and B, because we want to account for the smoothness of the shift or smoothness of the transition. Transition from 0 to 1, okay? Y equals to 0 to Y equals to 1, and with some shifting element that we might have in our data. So generally this might be equal to 0. It's nice if we have that case, but it might not be the case, okay? Great, so this is exactly our sigmoid function. Now let's look how we're formulating this problem. So we have our sigmoid function, and this is our prediction, okay? So here what we assume, if we go back, so it's exactly similar to the previous case where we had our linear regression. So this is, for example, our xi. This is the ground truth, yi. And where is our prediction here? So the prediction is the fit by this curve, right? So our prediction. So what we assume that our prediction yi, so we assume that actually not the prediction, so the prediction is right here, okay? It's equal to the sigmoid of this point, right, of this xi w plus b, our new point, but we assume that the ground truth is very close or can be approximated by this sigmoid function. So it's exactly the same concept, okay? Now let's look at this more closely. So we need to define our loss function, right, if you guys remember. So we have our xt vector, so that belongs to rd. This one also belongs to rd. And we have a scalar b vector, a b value. So that's the shifting our shift factor, okay? And this is exactly our loss function. So here we have the predicted point by our sigmoid function, okay? For our observation xi, or our feature vector xi, and the ground truth, and we're computing their distances, okay? N squared. So that's, you know, the least squares cost function that we want to minimize. And our cost function depends on two parameters, the w and the b, as same. And here, in a very similar way, we define the compact form. So by defining a new variable or a new feature vector xi tilde, we change this formula. So we remove somehow the b, and we get just simply sigma xi transpose w tilde minus the target value. Okay, so quite simple. Now let's look at the derivation. So what I would like you guys to do, I'm not going to show you the math, I'm going to give you just 1 minute or 2 minutes, okay? And I would like you to write the gradient of this loss function. So compute the gradient, and I'm giving you a hint that will make everything easy for you, okay? So try to write it down. I'll give you 1 minute. So we're applying exactly the same rules. And when we're deriving this function f, this is what we get. And oops, there is actually an x that is missing here. Okay, so let's look at the solution. So basically, I have expanded the squared form right here, okay, as usual. Then we're going to derive those, like the first one and the second one. The third one is equals to 0 because it doesn't depend on W tilde. So for the first one, you guys can see this is just, you know, a derivation of a squared function, right? So we have first the 2, so that's 2 times, so we have f and f prime, okay? So f prime, this is exactly right here. So it's the partial derivative of the sigmoid function with respect to w. And then here we have minus 2, so this is minus 2, and this is the derivative of the sigmoid function, okay? Right there. Great. So next we just, you know, put everything together. But what you guys can see by putting everything together, ultimately we get this function that is quite complex, right? So it has many elements, right? So it's like it's multiplying all these terms. And here, even if we set it to 0, it's not obvious, it's not easy to derive what we call a closed form. So if you remember previously, when we solved the linear case, the W was very obvious. We can easily derive it, right? But here, even if you write, you know, so here, like, you know, the exponential function, the sigmoid function, so you write all the terms, you do everything. It's not easy to have a closed form solution for our W tilde. So what is the solution in this case? We do gradient descent, okay? So we computed the gradient. We can plug everything in. So the idea is like this is not, we can derive a closed form. So we just resort to the typical scenario, which is using gradient descent. So we computed the gradient. We start with an initial point, W tilde 0, okay? Compute the gradient, move downward, and doing that over and over again, okay? So this is one possible way of solving this, the logistic regression problem. So next, let's look at this. So here, what do we have? So in this example, we have our input variable x. So these are our input, our feature vector, but in this case, it's just, you know, just a simple case. We don't have a high dimensional vector, and we have a target output y, and you can see that the relationship between those two variables, the input and the output variables, fits nicely a sigmoid function, right? So in this case, by plotting the data, we will formulate this problem as a logistic regression problem and compute the loss. And here in this example, we plotted our loss function in which depends on the two variables w and b, and you can see that locally here it has a minimum, right? So the minimum is around there. And what we did, so in this example, we have two different initializations of the gradient. So first we take this point as initial point, so W0, B0, right? And for the purple curve, we had another initialization using another point. So what we noticed that using the purple initialization, we have a good fit. So we have a good estimation of the logistic fit to our data distribution. But in the second one, for the green one, we have, it's still logistic regression, but we have like a very flat line. So you can see that the gradient, like it moved downward, you know, down this direction, but it got stuck, okay? And this is very visible here. So we have a flat region. So the orange region is very flat. So our gradient, our initialization wasn't good enough. So it got stuck right there, okay? So you can see that optimizing the logistic regression function is not very straightforward. It's very sensitive to your initialization, okay? Because remember why? It's a non-convex function. Right, now our solution here depends on the initialization, right? And the gradient descent, the initialization of a gradient descent algorithm. And also we notice that the initialization in the large flat orange region leads to a poor solution, a poor estimation of our fitting function. So Guys, this is the moment where you need to think, so thinking caps on, and I would like you to think about how can we improve basically this improve this problem. Like, how can we solve this problem? How can we get a better solution, right? So what is the main idea? I want you to compare those. So this is, the scenario where we had two different initialization. This is how our loss function looks. Okay, so the loss function we plotted in the function of its two variables, w and b, two parameters. Okay, this is a distribution of this is the relationship between the input data and the output data that we want to predict. In here, we have done something. So there is, if I will give you a hint. I would like you to compare the loss function in the first scenario, first case, and in the second case. So what has changed? It might not be very, very obvious, but we here notice that wherever we initialize, it doesn't, like the algorithm converges, it finds a good fit to the data if we initialize it in this region or the other region. So it doesn't really, it's not very sensitive to the initialization in the second case, right? What happened? What did we change? So maybe it's easier if you guys look at the contour plots of the loss function. So remember, the contour plots, it tells you, it visualizes and displays the shape of your function, right? How it looks like. And we know that the gradient descent, if we have parallel lines, if we have, for example, parallel contours, or if we have flat areas like here, we can clearly see them when using the contour plots of the function. So what do you guys notice? There is something that we did to the loss function. We changed something. So forget about the gradient, okay? So the gradient, we initialized it exactly at the same, green and purple points. The behavior has changed locally. So why the gradient now it works? Because exactly, it's not flat anymore, okay? So what we did here is, in this example, we say we made this area convex. So we curved it, right? We convexified it. So here we smoothed or convexified the problematic regions in the loss function, okay? So right here, you can also know, you guys can know this for the purple one, it used to go slightly down and then curve downward, but here it's like more smoother. So it's a smooth, basically it's rolling down smoothly, right? So here too, we looked at this function and all those problematic basically regions, like where there's like almost a stationary point, we made it more convex everywhere. So we convexified it, okay? So we curved it. And if we convexified it, which means, it means that locally it's a convex function. So the gradient descent, the gradient can move can move smoothly, right? Our walk along the steep direction is a smooth walk. How did we do that? Okay, so now let's look how did we do that. But before that, let's look at this example too. So in this example, you can see we have our original loss function. In the original loss function, we had the saddle point. So the algorithm might get stuck in this flat area, right? Because it's flat. So here we basically convexified it too. So we made it convex. Oops, something like that, okay? So this is actually changing the shape of the loss function locally. And you can see that even this, like the minimum, it changed a bit. So we convexified it a little bit, almost everywhere, right? And here, this is what we exactly did. So we added what we call a regularization term. Okay? So in flat areas, the regularization, the L2 regularization, it's just, the L2, we call it the L2 norm of a vector. So this is, the typical norm of a vector. It's like, your typical Euclidean distance, right? And then we just square it. So this is, we call it right here, this is the L2 norm. And we take the squared L2 norm of the weights, okay, of our parameters. So our loss function is this new loss function. So it's the original one, which is fit to data, samples, plus a regularization term, okay? So by adding this term, somehow, adding those weights, we made our global loss function slightly more convex in areas where the gradient might get stuck. Okay, so what is this norm? If you guys remember it, it's just the sum over all dimensions of the vector W, and these are the components or the weights, all the weights in our vector, and it's just a squared. It's a sum of squared weights. Okay, so that's the L2 norm. And here, what do you guys notice? Let's look at these different cases. So the first case is if we have lambda equals to 0. So here, I forgot to mention the lambda. So we have what we call a parameter lambda. It's a trade-off parameter. So the lambda is a trade-off. We call trade-off parameter. It's a trade-off parameter between two terms, between term 1, which is the fit to data term, and between the regularization term, okay? So if lambda equals to 0, we go back, we find the original case, right? So where we solve the nonlinear regression without any regularization. Now, if lambda is very, very large, it means basically this term, if this term is very large, maybe it's, 10 to the power of, I don't know, like 10, and this guy is so small, it's like 0.01. So if we make the lambda so big, right, then our minimization will be brought down to just minimizing the weight, like the L2 norm, okay? So in this case, we say that the regularizer, it drowns out the loss function. So they're like, the loss function is so smooth, like it kind of disappears, okay? So you don't want your lambda to be too small, and you don't want it to be too big, so you kind of neglect the real fit to data term, right? But you want it to be in between. So generally, typically, the lambda is set to 0.1, 0.01. So these are the typical values that the lambda would take to balance these two terms in the optimization process. Now, okay, so we looked at when we have problematic areas, how do we solve that? We add a L2 regularizer, and this is, because this is just a simple convex function. So adding a convex function to the parts where the original function is non-convex, it makes it slightly more convex. Okay, it convexifies it. So because we're adding a convex function to the non-convex function, it is smoothing it and convexifying it in problematic non-convex regions. Okay, so you guys now get the intuition and understand why regularization might be important. So let's look at this case. So in this case, you can see that with the regularization, when we added the regularization term, which fits into our learning model that we discussed, I think, in lecture 3. So you can see that we have a nice convergence of the algorithm and a nice behavior. We nicely find the optimum, and it does not depend anymore on our initial parameters. Okay? Great. So this is, guys, there are 2 practicing exercises in chapter 3 of machine learning refined. So I highly recommend that you look at exercise 3.11 and 3.13, where you will just fill in the code. So there are some missing parts where you need to write the gradient for the logistic regression in both with and without regularization. So please try to do that. It's a good training for you. So if you can get it right, it means, you really grasped, this whole lecture. Okay?